Last lesson we prepared the mesh using the program ANSYS, and now let's go on with calculations. We will use the component system, which is called Fluent. Put it on the table and export the model from ANSYS to setup of Fluent. And open it. We see that the dimension is 2D. The options are serial, we will not use parallel, and we will not use double precision for this test problem. Okay. The project is opened. We see our mesh. We may use the scale option if we want to change the dimensions of our flow region. We are using meters. I think all units are okay. Close it. We may also check the quality of mesh. The results are shown here. Report quality. Some results are shown here. We see that the maximum aspect ratio is about 22. I think it's somewhere here where the height of the cell is much bigger than its length in x direction, its width. But I think it will cause no problem. Then the parameters of the solver: pressure based, the task is steady, and planar, not axisymmetric. The next point of our work is models, setting up models. Let's open it, models, task page. Of course, we will change the energy, switch on energy equation, because the flow is supersonic, and also it consists of several species. Okay. For sure, we have the turbulent regime. So let's change the viscous model from laminar to, for example, K epsilon model. Let's try this turbulent model. All points we will take by default. Okay. No radiation, no heat exchanger, but we will use next the species point. Let's open it. We have several species in this task, so let's change it to species transport. Additional equations for species we will use. No changes. At first we will try only to choose the properties of mixture. Let's open this list and choose hydrogen and air. We will study the mixing of hydrogen and air. We choose it. At first we will not change anything, only the material properties, and click OK. We've got the information that relaxation factor has been changed for density. Next, I think the models are the setting models is finished. Now let's open the materials. We have the material mixture, hydrogen, air, and let's open this point. The name of this material mixture is hydrogen air, the type mixture, fluent mixture material the same. Let's look at what is the names of these materials. So click on the edit button. We have the following species: hydrogen, oxygen, water, and nitrogen. We may add more materials, but we will not do it, only use default materials. Then, by default, the density is incompressible ideal gas. Of course, it's not can be used for the supersonic flows. We will change it to ideal gas. It's more correct. All other properties we will not change. Specific heat, conductivity, viscosity, and diffusion coefficients we will leave the same as they are given by default. Click on Change Create button and close this material. The next point is to set the cell zone conditions. Material, we make sure that material is hydrogen air. It's okay. Let's open the cell zone conditions and see the operating conditions. I repeat, open cell zone conditions and operating conditions. We see that the operating pressure is about atmosphere in pascals, so it's okay. We will not change it. And now the boundary conditions. Some of them are set by default. For example, base 1 is wall. We will not change it. The same base 2. Bottom also is default type wall. And now inlet. It is more interesting for us, so let's open it. By default, it is velocity inlet. It's not good for supersonic flows, so let's change it to pressure far field type. Again, the type of inlet for the air is pressure far field. We take from the template article the data for this boundary condition. Here it is. Mach number for the air is 2, the temperature, the pressure in pascals, just the same as in cell zones. And the mass fractions of the species are given by these numbers. So let's set these numbers. This pressure is relative for the cell zone pressure, 1 atmosphere, so we leave there the 0 number. Mach number is 2, the direction in X component. Let's change the turbulence. Sometimes it plays very important role. We will use the method which is called intensity and hydraulic diameter. Hydraulic diameter. The intensity is 5 and hydraulic diameter is the width or is the height of the channel. We will set it something like 5 centimeters. The next, let's set the temperature. The temperature of the air is 340. And the mass fractions: hydrogen 0, oxygen 0.232, and water, hydrogen 2O, is 0.032. 0, 0, 2, 3, 2, and the next for the water. Okay. The inlet of hydrogen will also change the type to pressure far field. The Mach number is 1. The component of x in x direction is 1. Also, let's use the for turbulence intensity and diameter. The dimension of hydrogen inlet is much less than of the air. It's about 1 millimeter. The next is thermal. The temperature is 250. And the species only hydrogen 1. Okay. The next boundary condition is outlet. In this case, we again use the pressure far field boundary type and put the same values as air inlet. So 2, the same turbulence parameters, thermal 340, and species just the same as for air inlet. Okay. I think top is set by default is default type is wall, and the same for wall 1 and wall 2. We will not change the boundary type in these cases. The next point of our work is initialization. But at first, let's look at what methods which are used in this task. We use the most completed, very good method coupled, in which all equations are solved at the same time. For pressure, we use second order special discretization. The same for density, for momentum, and for energy. And for species, the second order. For turbulence, by default, the discretization is set to first order. We will not change these options. So let's begin initialize our task problem. We will use standard, and we shall compute it from the air inlet. So again, initialization, standard initialization, compute from inlet, and click on this button, initialize button. And now I think we may begin our solution run calculation. Open this option. Change the number iteration. I think we may begin from 100 iteration for the first calculation and click calculate. We see the residuals, scaled residuals changing for all our equations, for continuity, for momentum equation, energy. The most cause is continuity equation. One current iteration, I think we may continue and make one more calculation. Also, yeah, let's change the number of iterations to 300 and calculate. In this case, we are using the values which as in previous solution and the initial values. So the solution continues. It's very soon finished. And let's try to look at the results. For this case, we using the option results. The most interesting at first is to look at the contours of the parameters. Open it by double click. The pressure is offered to show. Let's do it. Save and display button. Oh, it's very interesting. We have some results of the from literature. The shadow picture of this flow in case when there is no reactions, no combustion. No, it's not very much alike, but I think that the position of main shows not very much alike, but we'll compare the other values later. Okay, let's look at temperature, at first velocity, especially the velocity in x direction, contours of velocity, x velocity, save and display. The boundary layer on the walls is very coarse because the height of the mesh is very big. Let's look at y velocity component. The flow at first goes down from up. The direction of the hydrogen jet, at first it enlarges. Now the temperature raised somewhere behind the shock bows, behind the shocks. The biggest temperature is 400, more than 400 degrees Kelvin. Now let's look at turbulence quantities. The turbulent kinetic energy. The biggest value is near the mixing layer of hydrogen and air, at the beginning of jet. Then dissipation, epsilon. It is very much alike. Let's look at turbulent viscosity, very important value. Very interesting. The biggest values is behind the shocks, not in the mixing layer. What more we can see? Oh, the species. The mass fraction of hydrogen. Of course, it's near its inlet. And it varies from 1 to 0. So let's close the contours and try to find, for example, path lines. Let's open this point, path lines. Not particle variables, but velocity, interesting for us, velocity magnitude, let it be. And start it on inlet and inlet H, no, at first inlet simply. Show. Maybe I will change the number of passes. It's more interesting to show how the air moves in this channel. Let's look at the velocity passes of the hydrogen. Oh, it's because, of course, no, it's not very interesting to see it. Close. And let's try to build some plots. We select XY plot. And let us see how the pressure varies, for example, on the bottom wall. Select bottom. The plot direction is X. And let's try to see. So it changes something like in this manner. We may compare it with the experimental data from the same article. The distribution of pressure near the wall is shown on this picture. Let's use not static pressure but absolute pressure. It's more information. It gives more information. Yes, now it's good. Open again the experimental data. The beginning of this is not the same as in our calculation. It begins from the right part of the left part of the flow. But the character is the same. The maximum pressure is about 2 atmospheres. But this value, the low value is about half of atmosphere. In our calculation we've got much more value, and the same is for the second peak of the pressure. In the experiment we have about 1 and 7. Oh yes, and we have only about 1 and 2. much less than an experiment. I think it's because we must build more fine mesh near the walls, and we will get, I hope, better result. But for the first calculation for coarse mesh, I think it's okay. It's for, we make the calculation of the flow without chemical reactions. On the next lesson, we will study the chemically reacting variant of this problem. So let's finish this part of the solution.